compared with the flow of electrons through a circuit. And it is possible for you to learn to control the flow of current just as a skillful player controls billiard balls. There is no such thing as a perfect conductor. Even the best conductors, such as copper and silver, have some resistance, even as the smooth table offered some resistance to the billiard balls. Other conductors have much greater resistance, such as iron, manganese, and nichrome. Resistors which are especially manufactured for the purpose have a resistance just high enough to limit a certain flow of current a desired amount. The billiard table may be used in another way for comparison with a conductor. If the same number of balls which were before moved down the full width of the table are now forced down the width, or I, let the force of the billiard cue represent the voltage, or electromotive pressure, E. Let the resistance of the table represent the resistance, R. Then the number of balls in motion equals the force of the cue divided by the table resistance, or I equals E divided by R. Thus, Ohm's law is illustrated. Table, suppose you have electrons in an electrical conductor. Instead of being propelled by a billiard cue, the electrons are forced along by the pressure of the voltage in the battery. A resistor is connected in series with the circuit in order to limit the amount of current. The circuit is now broken, and there can be no steady current flow. However, there is a tendency, ever so slight, toward a displacement or strain in electron placement, which results in a concentration of electrons somewhat higher than normal at point A, and a lower concentration by an equal amount at point B. At the point of break, large plates of conducting material are attached with only air between them. The air, of course, is an insulator. The displacement or strain will now become greater. There is a movement of electrons away from plate B and toward plate A. This is because the positive battery terminal attracts electrons from B, and the negative terminal repels electrons toward A. You may say that A is being filled with electrons and that B is being drained of electrons. Since at B there is a lack of electrons, B may be considered positive. And since at A there is a surplus, A may be considered negative. The surplus electrons at A would like to get to B, but are prevented by the air, or insulating material between B and A. This causes an electrostatic stress between A and B. When the point of stress is reached where the voltage charge across A and B is equal to that of the battery or other voltage source in the circuit, no further electron movement occurs, or no current flows. It is very important to understand that work was done in order to charge the plates, and that current flowed even though the circuit is not continuous. Now, if switch S is opened, or the condenser is completely removed, the plates A and B will maintain their charge. The escape of the electrons at A is cut off. If the plates are made larger, more energy can be stored. You could say that the larger plates have a greater capacity, or that we are dealing with a larger capacitor. When a conductor is placed between the leads from plates A and B, the surplus electrons at A will rush through the conductor to B until A and B are equalized. Thus, the capacitor has been discharged. A capacitor, then, has the capacity for storing electricity, and it takes its name from that fact. Since the electric current is forced into it from a voltage source and is stored under pressure, the capacitor is commonly called a condenser. A condenser may be compared with an automobile tire. Air is stored under pressure in the tire. With a gauge, the amount of air stored under pressure can be measured in units. If more air is pumped into the tire, a greater pressure will, of course, be registered. The tire has a maximum capacity. If more than the maximum amount of air pressure is applied, the tire will burst. When the valve is opened, the air rushes out of the tire, and the air pressure within the tire is equalized or balanced with that of the normal air pressure outside. The capacity of the condenser can also be expressed in units. These units are called Farads, microfarads, or microfarads. The capacity of the condenser can be likened to the cubic inches of space within the tire. When the condenser is connected to a voltage source or power supply, the ammeter shows that a current flows, charging the condenser until the opposing pressure is equal to that of the voltage source. Now the voltage is increased. The higher voltage will overcome the opposing pressure in the condenser, and the condenser will take more charge until the opposing pressure is again equal to that of the voltage source. Voltage, E, times capacity, C, equals Q, which represents quantity of electricity stored in the condenser. If too great a voltage, or electric pressure, is applied across a condenser greater than its strength can withstand, the condenser will be ruined. A great variety of types and sizes of condensers are used in radio and electrical work. In general, condensers vary in their characteristics and degree of capacity in three ways. First, the plate spacing. If a condenser of a certain capacity could be adjusted mechanically so that the plate spacing were doubled, the resulting capacity would be only half that of the original. On the other hand, if the plate spacing were to be made only half as great, the attraction would be doubled and the capacity would be increased. Second, the plate area, as you already know, affects the condenser's capacity. If the plate area is doubled, then the capacity is doubled. Or if the area is reduced to half the original amount, the condenser will have only half its original capacity. Third, the dielectric, or insulating material used between the plates, affects the capacity of a condenser. Air is a common dielectric. However, other dielectric materials, such as mica, which are more dense than air, can be used. They will increase the capacity of a condenser just as though the plates were made larger or the distance between them reduced. If some sort of plastic material is used instead of air, it may more than double the capacity. The plastic material is said to have a higher dielectric constant when compared with that of air. When glass is used between the plates, it has a still higher dielectric constant and gives the condenser a capacity from 4 to 8 times as great as when air is the dielectric. When parallel plates are added to a condenser, the effect is the same as increasing the area of two plates, for the total dielectric area has been increased, and therefore the capacity of the condenser is increased. When condensers are connected in parallel, the effect is to increase the capacity. When two or more condensers are connected in series across a source of voltage, the voltage divides among them, and the total capacity is decreased. Discharging several condensers will demonstrate the equalization or balance of electronic pressure within the circuit. These three condensers will be charged from the same voltage source. When the first condenser is discharged, a very small spark is formed as the surplus electrons rush from one plate to the other. When a larger condenser is discharged, a larger spark is formed, showing that the capacity of the larger condenser is greater, and therefore a greater quantity of electricity was stored. As the largest condenser of the three is discharged, you can see for yourself that its capacity is still greater, and that more electricity was stored. Here is a circuit with a 6-volt battery, a 1-ohm resistor, and a condenser connected in series. The circuit is broken by the open switch S. A difference in potential of 0 now exists across the condenser, so that at the instant the switch is closed, the condenser appears to be a perfect conductor, and the resistor offers the only opposition to the current flow. According to Ohm's law, the current I equals a voltage E divided by the resistance R, or I equals 6 volts divided by 1 ohm, or current I equals 6 amperes. An instant later, however, assume that the condenser has taken on half of its charge, or 3 volts. So the current flow is now decreased to 1/2 of what it was originally. Still an instant later, the condenser has taken on half of the remaining possible charge, so the current flow is decreased to 1/4 of what it was originally. For practical purposes, you can say that the condenser becomes charged. The time this takes depends upon the amount of resistance in the circuit and the amount of capacity. The current flow through a resistor in charging a condenser in a circuit like this one can be illustrated by a graph. The horizontal line is marked off in units of time. These can be seconds, hundredths of seconds, or millionths of seconds. The vertical line represents the amount of current flowing. As the condenser voltage builds up a greater reactance, it opposes the battery voltage. During each unit of time, the current flow is reduced a certain percentage of what it was during the preceding unit of time. By connecting these points, a curve is produced which gives a picture of the amount of current flowing at any instant during the charge or discharge of a condenser through a resistor. In the same way, the voltage built up as a charge across the condenser can be pictured by a curve. At first, when there is no condenser voltage to react against the battery voltage, the charge across the condenser builds up very rapidly. Then it increases more and more slowly as the condenser charge becomes more and more nearly equal to that of the battery. The voltage of a discharging condenser can also be pictured by a curve. Now, since a condenser charges or discharges through a resistor, and the resistor affects the amount of current which flows through the circuit, there must be a relation between the size of the resistor, the capacity of the condenser, and the time it takes the condenser to charge or discharge. A very simple fact has been found, that the resistance in ohms times the capacity in farads is always equal to the length of time it takes the condenser to reach a certain percent of its full charge or discharge. As can be shown on the graph, this is the time it takes the current to fall 63.2% from its maximum value as the condenser is charged. This point on the graph, then, is called the time constant. It may be calculated by a very simple formula. T equals R times C. A complete curve such as this one may be calculated for any given values of capacity and resistance by using a formula which is fully explained in the discussion film that accompanies this motion picture. Since resistance, R, times capacity, C, always equals the length of time it takes the condenser to reach 63.2% of its full charge, R times C is spoken of as the time constant. When the condenser is discharging, the current falls 63.2% from its original value after a time equal to R times C. By means of this demonstration board, the effect of the time constant, R times C, will be shown in charging and discharging a condenser. A source of voltage source is cut out of the circuit, and because the condenser will now be discharged, the meter must be reversed by means of this switch. The condenser is now discharged. It discharges rapidly at first, and then more slowly. The time for discharging the condenser until the amount of current falls 63.2% from its maximum value was 8 seconds, or the same as for charging it. As the condenser is charged again, Watch carefully and check the time in the clock when the ammeter shows that the current has reached the time constant indicated on the dial. As the current decreases, the voltage across the condenser falls. The resistor, R, has a resistance of 500,000 ohms. The condensers, C, have a total capacity of 16 microfarads. Since T equals R times C, the time constant is 8 seconds. If it is desired to find the amount of the current flow at any other instant during the charge of the condenser, it can be found in the formula given in the discussion film. The time constant can also be demonstrated on an oscilloscope. The oscilloscope is connected to the demonstration board. In this way, the same values can be used for voltage source, resistance, and condenser capacity as were used in the demonstration with the board. The oscilloscope produces a spot of light on the screen. The spot is moved vertically by the amount of current used to charge the condenser. Thus, the starting point of the spot shows maximum current, and as the spot comes down, it represents a smaller and smaller amount of current, just as it was represented by the ammeter. The movement of the spot to the right represents the amount of time the condenser takes to charge or discharge, just as it was represented by the clock. The movement of the spot traces a curve, like the one used on the graph. Since the spot can be made to move very rapidly, the oscilloscope makes it possible to see what happens when the time constant is small and the condenser is charged and discharged too rapidly for you to follow using the meter and the clock. A curve can be calculated by means of the formula given in the discussion film and using the same values for R and C that are used in the demonstration board and the oscilloscope. This curve can be traced on the screen of the oscilloscope. You can see that the spot produces the same curve as that on the graph. This mark represents the time constant, or the point where the current is down 63.2% from its starting or maximum value. Now one condenser is disconnected. The condenser remaining in the circuit has only half the capacity that both condensers had. Watch the meter and the clock. You can see that the time constant is only half as great as it was. Now the resistance is cut in half. You can see that the time constant is still further reduced. It is only 1/4 of what it was originally. Now the resistance and capacity are both made much smaller. The time constant becomes very small. That is, the time of charge and discharge is very, very short. It is in fact so short that it's impossible to time it. Yet the shape of the curve remains the same. You can now understand that the condenser stores electricity. The resistor regulates its flow. Together they form a team which makes it possible to control the expenditure of the stored electricity over any desired interval of time. In this circuit, when the switch is closed, the condenser immediately begins to charge. Because of the resistor, it cannot charge instantaneously. Consider what would happen if at the beginning of the second period, when the condenser has a 3-volt charge, the battery is suddenly reversed. Now the condenser is discharged, and the 3-volt negative charge in the condenser is aiding the battery instead of pushing or reacting against it. A heavy current flows in the opposite direction. Now at the beginning of period 3, another reversal of battery polarity takes place, and this is repeated with a reversal each period. As a result, except for the instant of reversal, there is current flowing in the circuit at all times. Although it actually doesn't do so, for all practical purposes, this alternating current appears to flow through the condenser. The same thing holds true with alternating current from any source, and also with any fluctuations in direct current. If the frequency of reversal of the current is very low, the condenser is much less like a conductor, for the amount of reactance it offers to the battery voltage is greater. But as the frequency increases, the reactance becomes less and less. You remember that a condenser blocks direct current. You can now understand why it is said that a condenser passes alternating current. This ability of a condenser to block DC and pass AC has a number of important uses. One of these uses makes it possible to amplify my voice as you're hearing it right now. This is done with several audio amplifiers. This is a microphone amplifier. It has 2 vacuum tubes, which provide the first 2 stages of amplification of the voice signal, which is alternating current. This is a diagram of the amplifier circuit. As you know, a vacuum tube must have a DC positive voltage on its plate in order to operate. Amplifiers of this kind usually must have DC negative voltages on the grids of the tubes. Yet, the alternating current representing the voice must be conveyed from the plate of this tube to the grid of this one. The condenser between serves to block the positive DC voltage and thus separates it from the negative DC. At the same time, it lets the AC, representing the voice, pass through. You can appreciate that the principles of resistance and capacitance are very important factors in radio and electrical work. Along with inductance, they are the principles that form the foundation for all radio apparatus. You now have an overall view of resistance and capacitance. This motion picture is accompanied by a discussion film, which the instructor can coordinate conveniently with lectures. It is suggested that the 2 separate sections of this movie be run individually as needed during concentrated study and review of capacitance. It may help with those exams.